elements, compounds, mixtures, right? So when we talk about we go over elements, compounds, and mixtures. First, let's go ahead and discuss what would be the possible difference between these three. What is the difference between an element, a compound, and a mixture? So when we start by talking about an element, what is an element? An element is a substance that cannot be split into anything simpler by chemical means. Chemical means is the important term over here. I can split an atom into smaller pieces. I can take an atom and I can break it down into smaller pieces. I can definitely do that. But I cannot do it by chemical means, not chemical, right? How do we actually split open an atom? How do I break an atom apart to take a look at the internal structure of an atom, the protons and the neutrons? For that, I generally need the help of physics. I can't do it chemically. I will need to go for physical means, right? So an element is quite simply put, it is a substance that cannot be split into anything further. It cannot be broken down into anything further without the help of my physical means. I cannot do it by using any chemical means. That is what an element is. So for example, if you open up your periodic table, we have the entire elements in front of us, right? We have our all of the elements. We have our metals, sodium, magnesium, calcium, copper, zinc, phosphorus, oxygen, sulfur. All of these are elements. What is compound? Compounds are formed when two or more elements chemically combine. When two or more elements are combining chemically, meaning that there is a chemical reaction happening between the two of them, right? That is a compound. And remember this, that in a compound, the elements are always in fixed proportions. What do I mean by that? That means if I will have one magnesium, for example, I have carbon dioxide. So carbon dioxide will always have one carbon and two oxygen. H2O, it will always have two hydrogen and one oxygen, right? The ratio between the elements is fixed. There will always be a certain number of the elements. If I'm talking about my sodium hydroxide, there will always be one sodium, one oxygen, one hydrogen. What about copper sulfate? One copper, one sulfur, four oxygen, right? So the compound, the ratios or the proportions of the elements are fixed. This is why diamond, would you consider diamond a compound? Diamond is technically not a compound.
It's an
Why
element.
is diamond?
It
Sorry,
only
say it again.
consists. It's an element. It only consists of carbons,
Yes,
right?
it only consists of carbons, right? It only consists of carbon. Not only does it only consist of carbon, but the number of carbons are not fixed. Okay? The number of carbons are not fixed. Now, let me tell you, there is, and we will study this when we do the topic of bonding, inshallah. There is something known as C60. C60
Mhm.
it's a
Mhm.
molecule. Now, this is also made of just carbon. That's it. It only has carbon inside, right?
It's the ball
But
type
this
of
is,
structure.
yeah, this is a molecule because the number of carbon atoms are fixed, 60, right? So that is another sort of important distinction. Diamond, that's another reason why diamond is not a compound. Not only is it that it only has just one element inside it, but also because the number of carbon atoms are not fixed. Diamond can have any number of carbon atoms. The greater the number of carbon atoms, the larger your diamond is. You
Okay.
can have molecules like C60. C60 also only has carbon atoms inside of it, but the number of carbon atoms are fixed. What about sulfur? Sulfur has a formula of S8. Or chlorine, Cl2. Or hydrogen. These are all molecules, right? They're not compounds because they only have one element, but they're still molecules. Why? Because the number of atoms are fixed. So when you are going to have two or more elements that are chemically combined, this is important. They need to be chemically combined. They will be considered an compound. And these elements will always combine in fixed proportion. Then we have a mixture. A mixture is always going to be different elements. It's always going to be different elements or different substances, but there will be no chemical reaction that is going to be occurring between them. Meaning that I can have, take a look at the air around us. The air around us is a mixture of gases. It has nitrogen, oxygen, carbon dioxide, argon, krypton, so many different gases, but they all do not chemically react with each other. Nitrogen is separate, carbon dioxide is separate, oxygen is separate. All of these gases are separate from each other, right? So that is a mixture.
Mix like
Now,
sugar and water.
uh, uh, a mixture, yeah, you can make a mixture with water. If
Okay.
I take sugar, yeah, if I take sugar and I mix it in water, so that's a mixture. The sugar is not reacting with water. I'm not getting sugar plus water is giving me a product, right? Do I
Anything
get
that
a different?
combines without a chemical reaction is known as a mixture.
Yes, anything that's combining without any chemical reaction. And in a chemical reaction, you will get a different product. The reactant will be different and the product will be different. If I take sodium chloride, salt, and I dissolve it in water, that's a mixture. Because sodium chloride is not giving me a different product. My product is the same. But if I take that water and I mix it, for example, with an acid, right? Or I mix it with some salt and I get a different product, I get sodium hydroxide or something like that, then that would be a chemical reaction. That would not be a mixture. Now, so the differences, what are the differences that exist between a compound and mixture? In a compound, the composition of elements present in a compound is fixed. So a compound, for example, if you have carbon dioxide, that is going to have one carbon and two oxygen. In a mixture, it's not fixed, right? I can have different oxygen, different nitrogen, different carbon dioxide, different argon, different krypton in the air. The composition is not fixed. In a compound, the properties of a compound are different from those of its element. What does that mean? If I take carbon and if I take oxygen and I react the two of them to get carbon dioxide is a compound. Carbon has different properties. Carbon is solid in nature. It is generally black in color and it has got different properties like it can conduct electricity in different forms, right? Oxygen is a gas. It is generally, it's got different chemical properties. It does
Miss
different types of
NaCl,
chemical reactions. Right,
sodium
exactly.
chloride,
NaCl, sodium is a metal, chlorine is a gas, but react the two of them together, you get a salt that has different properties, right? So
terrible.
in a compound, the product will be different than the elements. Carbon dioxide is different than carbon and oxygen both, right? So
Yeah.
compound, it's going to be different than its elements. In a mixture, you're going to have all of the properties. So if I take air, I can get properties of nitrogen and oxygen and carbon dioxide, and I will get the properties of all of them without actually, without any change. I will get properties of all the elements. All the elements that are present in the mixture, I will be able to get all of their properties. Then a compound, its constituent can be separated by chemical methods only. What does that mean? That means that if I have a compound like sodium chloride and I want to break it into sodium and chlorine, I will need to use chemical methods. What is the name of a chemical method that you and I can use over here?
Electrolysis.
Yes, electrolysis. So I will have to go for something like electrolysis. Mixture can be separated from physical means. This would include your, this would go ahead and include simple distillation, fractional
Fractional
distillation, our
paper
chromatography,
chromatography.
right? Yeah, so we have got different physical methods. We'll go
Can
over them.
we not use filtration?
Yes, filtration as well. You can use
Okay.
filtration, distillation, fractional distillation, lots of different methods. We'll go over them, inshallah. Then a compound is always homogeneous in nature, right? Meaning that the compound homogeneous means, so for example, to understand the term homogeneous, imagine that you are mixing something up. Okay, when you are going to be okay, when you're going to go ahead and talk about it, when you're going to be mixing things up, so when you end up getting an even mixture, you will say my mixture is now homogeneous, right? It's completely even, completely distributed, equal distribution throughout. It's completely homogeneous. We don't have differences, right? It's not different. We don't have a different distribution when you're making, for example, when you're baking and you're mixing sugar in your eggs, for example, so the sugar is completely distributed within the eggs. It's not that one area of the eggs have a lot of sugar and the other area doesn't, right? So compound is always homogeneous. A mixture can be homogeneous or heterogeneous depending upon the mixing.
Okay.
Now, let's go over our separation chemistry, the different techniques that we can use for separation, right? Let's go ahead and go over this. So, when we talk about separation, okay, let's first start by talking about pure substances, okay? Pure
Mm-hmm.
substances, like you studied the last time as well. Pure substances have a fixed melting point and have a fixed boiling point, right? However, so pure elements and pure substances, compounds even, they have a fixed melting and boiling point. On the other hand, a mixture will melt or boil over a range of temperatures. So for example,
Okay.
I have a mixture of sodium chloride, okay? Or I have a mixture of sugar and water. So the sugar will start to boil at its own temperature, whatever the boiling point of sugar is, it will start to boil at that. Water will start to boil at 100 degrees centigrade. So I will not see one specific boiling point. I will end up getting a range of boiling points. If you remember, I told you in states of matter that your impurities lower the melting point and raise the boiling point. The boiling point will increase, but the melting point is going to decrease. So a melting point and boiling point is really important if you want to determine a substance is pure or not. If you want to figure out if the substance you are getting is pure or is it impure, is it mixed with impurities, always test for the melting point and boiling point. If it melts and boils at a specific temperature, that means you have a pure substance. If it is melting and boiling over different temperatures, it was boiling at 70 degrees centigrade, then it also started to boil at 100 degrees centigrade, then it was boiling at 120 degrees centigrade. So it's boiling at different temperatures. Generally, that means that you are dealing with some kind of impurity, you are dealing with some kind of mixture. So that's how you will be able to identify the possible differences between a pure substance and a mixture. Now, question comes is that how do we separate a mixture? Because you and I just discussed that a compound can be separated by, for example, electrolysis. Not just electrolysis. Remember when we did extraction of metals, so we talked about reduction. Remember we were using carbon coal, right? The
Yes.
point is that I need to do some kind of chemical reaction. Whether I'm using carbon, doing reduction reactions with carbon, or I'm doing electrolysis, or I'm doing some other chemical reaction. The point is that I will have to do some kind of chemical reaction. But a mixture can be separated from physical means. What are the physical means that we can use? So the easiest one is obviously filtration. Now, this, if you remember these small points, it will be easy for you to solve questions on this. Filtration can be used to separate a solid from liquid. So if you have a question in which you have a solid and a liquid, choose filtration, right? If you have a solid and a liquid, automatically choose filtration, right? This is the apparatus we use for it. We generally have a beaker, okay? And then I'm going to put on top of it, I'm going to place my funnel. Inside the funnel, we place a filter paper. I will pour my mixture over the funnel. So what's going to happen? The sand particles will get trapped in the filter paper. They won't be able to pass through the filter paper because the filter paper has really, really small gaps. The pores in the filter paper are extremely small. The sand particles are not able to cross through. They will stay behind in the funnel. The water, on the other hand, will be able to cross the filter paper and they will be able to end up inside the beaker. The sand will be known as the residue. The substance, the solid that will get left behind in the filter paper is going to be known as the residue. And the liquid that will collect at the bottom is going to be known as the filter. So if you have a solid and a liquid, situation is super easy. Just do simple filtration. Situation becomes complicated when we have a solution. When it's a solid and a liquid, very easy, super duper easy. Go for filtration, right? But what if we don't have a solid? What if I have a solution? Now what will I do? Over here, then I have different options. I can go for crystallization or simple distillation or fractional distillation, right? When
Mhm.
will I do what? When will I use this and when will I use that? If you want to separate the solute from the solvent, what does that mean? That means that let's say you have a sugar solution. You get rid of the water, you remove the water, and you get the sugar. You remove the water and you get the sugar. So if you want the sugar but not the water, you go for crystallization. Right? If you want just the sugar, I don't want the water. I don't care about the water. The water can evaporate away. Fine. Go for crystallization. I just wanted the sugar. I just wanted the solute. But what if you wanted to separate both the solute and the solvent? You don't want to lose the water. You're saying, listen, I don't want to lose the water. I want the water to be separate and I want the solute to be separate. I want to take my solute and I want to take my solvent and I want to separate them. I want to keep both of them. If you want to keep both of them, then you will have to go for distillation. Right? And then we have fractional distillation. Fractional distillation is going to be in situations where, again, you want to, okay, over here, you had a solute and a solvent, right? You had a solute and you had a solvent. Fractional distillation is when you don't have a solute and a solvent. You have a solution, but that solution is made up of two liquids. Miscible liquids. Miscible liquids are liquids that are going to be completely mixed in with each other, right? So if I have a solution that's made up of two liquids, especially miscible liquids that are completely mixed in with each other, that is fractional distillation. If I have a solute and a solvent, a solution made of a solute and a solvent, and I want to keep both of them, that is simple distillation. If I have a solution again with solute and solvent, and I only care about the solute, I only want the solute, that is crystallization, right? So these are the different methods that we are going to be having. Okay. Now, crystallization is a method that we studied quite well when we did the topic of acids and bases and salts, right? Whenever I want to keep my hand on a hydrated salt, right? Whenever I wanted to keep my hand on a hydrated salt, so we studied two kinds of salt. The one that would form an insoluble salt and a soluble salt. Insoluble salt would form a precipitate. So I could separate it by using filtration. That's what we had studied. Just give me 1 second. when we have a soluble salt, right, we're going to have to go for crystallization. What had we studied in the process of crystallization? We had studied that we will take an evaporating basin. Then in that evaporating basin, we are going to put our solution. After adding our solution into the evaporating basin, we're going to heat it slowly. We're going to heat it slowly. Now, if you remember, we had studied that we do not want to evaporate all of the water. Because what happens if we evaporate all of the water? If we evaporate all of the water, we are going to end up with an anhydrous salt, not a hydrated salt. We are going to end up with an anhydrous salt, a salt with no water of crystallization, a salt that will have no water of crystallization whatsoever. So we want a hydrated salt, which means that we will heat the evaporating basin at a slow heat to boil some of the water.
Like we want crystals. If we will heat it all of it, we won't get crystals. We'll get a salt.
Sorry, say it again.
We want crystals, and for crystals to form, we need a little bit of water or moisture present. If
Yes,
we heat all of the
exactly.
water, we'll just get salt.
Yes. Yes. You get anhydrous salt. You will just get powder. You won't get
Yeah.
crystals. You will just get powder. Right? Then that's not crystallization. So what are we going to end up doing? We're going to have to heat it slowly. When we will heat it slowly, what's going to happen? We're going to keep on heating it until we get to a saturated solution. That's the key. We get to a saturated solution. Once we have a saturated solution, we will turn the Bunsen burner off. We will remove the heat and we'll allow it to cool. And when we will cool, the crystals will form. So that was crystallization. Now, simple distillation is a process that we can use when I want to separate a solute and a solvent, but I want to keep both of them. I don't want to evaporate any of my water. I want to keep some of my water. So I can do crystallization for sodium chloride solution. What will I end up getting? Crystals of sodium chloride, right? I can do simple distillation with the same solution, sodium chloride solution. But I want to keep the water. I don't want water to be evaporated away. I want to keep my water and I want to keep my sodium chloride as well. So we use the method of simple distillation. Simple distillation works like this. I'm going to be applying heat. When I'm going to be applying heat, this is a round bottom flask. The type of flask you see in front of us, we call this a round bottom flask. This round bottom flask is connected to a condenser. This type of condenser that they have shown us is known as the Liebig condenser. There are different types of condensers that we have in chemistry. This one is specifically a Liebig condenser. The Liebig condenser works like this, that what's going to happen is I'm going to apply heat. When I'm going to apply heat, when I reach the boiling point of water, 100 degrees centigrade, the water will start to boil and turn into gas. When the water will turn into gas, the gas is going to move into the condenser. I always move the water into the condenser from the bottom side and out of the condenser from the top. There's a reason for that. There's a reason why the water is put in from the bottom and water is taken out from the top. I mean, theoretically speaking, if you think about it, it seems much easier to put water in from here, right? Because water in from the top, right? But no, we need to put it away from the bottom. Why do we need to put it in the bottom? Because if I will just put it in the top, what will happen? The water will simply fall down and come out. That's not what we want. We want the water to swirl around. We want the water to surround the tube inside and then come out. Right? So that's why we use a bit of pressure. We put a pump and the pump will put the water in. And the water will move in because of pressure and it will completely fill the condenser and then we will remove it. Why are we doing all this? Because we want to cool down the water vapors. So the condenser, the cold water in the condenser will cool down the water vapors in the condenser. What will happen? The water vapors will condense back. What was condensation? Gaseous state to liquid state. So our gaseous molecules will turn back into liquid state. As a result, our water vapors will turn back into liquid, turn into water. That water is then going to be collected off in a beaker. Eventually, in the end of it, what will happen? All of the water would be in the beaker. The sodium chloride crystals or the sodium chloride salt, in this case, you would have the salt, the powder, will concentrate, will stay behind over here. Or if you don't remove all of the water, we can eat crystals as well. We can do whatever we want. But the point is the sodium chloride crystals will be left behind in the flask. The water will collect in the beaker, and now I have both the things completely present. Now, what if we have a solution? So far we were talking about a solution where we had a solute and a solvent. What if we have a solution that is just made up of liquids? There is no solute. It's just liquids. Now, when I mix two liquids, I can have two situations. I can have miscible liquids and I can have immiscible liquids. What are immiscible liquids? Immiscible liquids are those liquids that when you will mix them together, immiscible liquids. Immiscible liquids are liquids that when you will mix them together, they will form two separate layers. They won't actually
Oil
mix
and
together.
water?
Yes, oil and water. The oil will come at the top, the less dense one will come at the top, and the more dense one will go at the bottom. Right? So oil and water. So these are immiscible liquids, right? If we want to separate immiscible liquids, it's an easy process. We use something that's known as the separating funnel. Okay, we use something known as a separating funnel. We have a tap at the bottom. This is my water and this is my oil. Okay, I will use a separating funnel. I will open the tap and the water will slowly drip out of the tap and collect in a beaker. Once all the water has dripped out of the separating funnel, I will close the tap and inside the funnel, I will have my oil. That's it. So whenever we have immiscible liquids, we use a separating funnel. A separating funnel is easy to use because the liquids are in two distinct layers. They're in two separate layers. So I open the funnel, the water drips down, and once all of the water has been removed, I close it, and that's it. The only thing left in the funnel is oil. But what if you have a miscible liquid? For example, we have ethanol, that's an alcohol, and water. They will completely mix in with each other, which means that you will not see two separate layers. You will end up getting a single solution. Now what? Now we are going to separate them by using fractional distillation. The concept of fractional distillation is what? Boiling points, remember? We studied about fractional distillation in
Yeah. A crude oil.
crude oil
Separation of
as
crude oil.
well as we studied it one place in another place as well, if you remember.
Um,
Not this year, in the previous years.
production distillation.
Air. Remember?
Yeah. Oh yeah.
How do we separate? This is how we separate air. Remember, we used to do fractional distillation of air as well. So if I want to separate air in a components, why? Because air is a mixture, right? And we can separate mixture with physical means. So if you remember, we had studied that we cool down the air until it turns into a liquid. And then we will do fractional distillation. So we do fractional distillation of crude oil as well as air.
Okay.
So so how does fractional distillation actually work? So I have ethanol and I have my water. Ethanol boils at 78 degrees centigrade, and of course water boils at 100 degrees centigrade. Now, what's going to happen that when I'm going to apply the heat, I will end up getting my vapors of ethanol. Okay. Now, the problem with the vapors of ethanol is that they're not pure ethanol vapors. I will also have some water vapor mixed inside of it, right? Because even though I'm not at the boiling point of water, even though I've not reached the boiling point of water, but we know that when we heat water, it starts to evaporate. So the water will be evaporating, right? Ethanol will be boiling, water will be evaporating. So I will get a mix of vapors, ethanol vapors as well as water vapors. Now, how do we separate the two vapors out? We use something known as a fractionating column. A fractionating column is generally filled with beads, marbles, small beads, small marbles, we generally fill it up with that. What
Okay.
happens? That so I'm getting a mixture right now of my ethanol vapor and water vapor. Now, what's going to happen that the ethanol vapor, since we have reached 78 degrees centigrade, since I'm at the boiling point of ethanol, so the ethanol vapor will simply move through the fractionating tower and enter into the condenser. What about the water vapor? I am not at the boiling point of water yet. So what's going to happen? The water vapor, as it moves through the cold beads, it will condense. It will condense and it will turn back into water and it will fall back into the bead. So the ethanol vapors, since ethanol is at boiling point, the ethanol vapors will travel up the fractionating column and go into the condenser. The condenser will work in the same way as before, and it will cool down the ethanol vapors and we will collect ethanol in a beaker. The water vapors, on the other hand, will not be able to enter the condenser. Why? Because the fractionating column will allow those water vapors to cool down. And since water is not at 100 degrees centigrade, so it will quickly turn back into liquid and fall back into the round bottle flask. So we can separate the ethanol and we can separate the water. All clear? Any confusion so far?
No.
Okay. Then we have another process that we can use for separating pigments. Chromatography is a process that is specifically used when we are dealing with colored compounds. That is your pigment. How does it work? What do we actually do? The first thing we need is a chromatography paper. Okay.
Okay.
We generally use a chromatography paper. That's the first thing I need. A chromatography paper or a filter paper, but generally we have a special paper that comes from it, chromatography paper, but we can use filter paper as well. Now, step number one, you will take this is your chromatography paper. At the very bottom of it, you're going to make a line with a pencil. Why are we making a line with a pencil? The reason we make a line with a pencil is because if we use ink, so ink is a pigment. So the pigments will move when we do chromatography. That's why you use a pencil. So the line doesn't move. The line stays where it is. Because if we will use ink, then the pigments in the ink will move up the chromatography paper and we will not get accurate results. So we always draw a line with a pencil. After that, I will go ahead and I will take my mixture and I will place it over here. Okay?
Okay.
That's step number one. Step number two, now I will go ahead and place my paper in a beaker. This beaker is going to have a solution inside of it. It's going to have that solution is going to be the solvent. Now, what solvent I use is going to depend upon what solvent I use is going to depend upon the pigment. There are different kinds of solvents we can have. For example, we have organic solvents as well, ethanol and all, they're organic solvents. So we can have organic solvents. So we can use different kind of solvents. The important thing is that the solvent needs to be below the pencil line. The pencil line we have drawn, the solvent needs to be below it. Why?
Okay.
Because if the solvent is above our pencil line is going to get smudged. We don't want that. We don't want our pencil line to get smudged. So
Okay.
we are going to make sure that the solvent is below our pencil line. Then normally what we do is that we actually put a glass on top of it, generally speaking, and or a lid on the top of it. And the reason we generally put a lid on the top is because we don't want any of the solvent to evaporate away. Now, after that, what is going to happen that we are going to sit and wait. We are going to let solvent travel up the water or travel up the paper. As the solvent is going to travel up the paper, it will separate out the different pigments inside the ink or inside the dye. Now, how does it actually happen? If you think about it, how is it that the solvent moving up the paper, how is it that this solvent that is moving up the paper is somehow able to separate all the pigments? How is that even working? How does it actually manage to do it? Now, this is a concept that's a little bit out of your syllabus, but I want you to understand the theory behind it. When we talk about our pigments, so pigments are what? Pigments are chemical compounds. Now, each chemical compound inside the dye, for example, we have over here the red pigment, okay?
Yeah.
So the red pigment will have a certain attraction towards the solvent and a certain attraction towards the paper. Now, the red pigment has more attraction towards the paper and less attraction towards the solvent. So as the solvent moves up the paper, the red pigment is attracted towards the paper more. So it will slowly get attached to the paper and it will fix. The green pigment, on the other hand, also has an attachment for both solvent and paper. But its attachment for the solvent is more than the red one. The red one, compared to the red one, it's a bit more attracted towards the solvent and not that much towards the paper. So it travels a greater distance compared to the red one before it finally becomes attached to the paper. The blue dye at the very top has a very strong attachment towards the solvent and weaker attachment towards the paper. So it travels a greater distance with the solvent before it finally adheres to the paper. Right? So the solvent will continue to travel up the page. Solvent doesn't stop. The solvent continues to travel up the page. The maximum distance covered by the solvent is going to be known as the solvent front. The maximum distance covered by the solvent is known as the solvent front, right? So we are going to measure the solvent front. Got it? Now, after that, we are going to have to end up. So this is what I was talking about. The dyes that make up the mixture have two important properties. The affinity they have for the paper, affinity is attraction, and how soluble they are in the solvent, which moves up the paper, right? So over here, you can see that the red didn't move much. Why? Because red's affinity for paper is greater and it's not very soluble in the solvent. So it only traveled a short distance before it actually attached to the paper. Blue, on the other hand, had more solubility. It was more soluble in the solvent and its affinity for the paper was less. So it traveled a greater distance with the solvent because it was more soluble in the solvent, right?
Yes.
This pattern that we get at the end, this pattern is known as chromatogram. Now, what if you have a pigment, right? You have a pigment, you have a dye, and you have separated the pigments from each other. You want to identify what the pigment is. How will you be able to identify? How will you be able to tell what pigment this is? To do that, you need to calculate something known as RF values.
Okay.
RF stands for retention factor. How do we calculate the RF value? To calculate the RF value, measure the distance traveled by your dye,
Okay.
right? The distance traveled by your pigment. Then divide it by the distance from the solvent front. So solvent front was the maximum height, the maximum distance traveled by the solvent. So if you calculate the distance traveled by the solvent and you calculate the distance traveled by the pigment and you divide the two of them, you will be able to get your retention vector or your RF values, right? And based on that, you are going to be able to calculate your retention factor. So this is how it actually works. So this is how it's actually going to be working. I will calculate the distance traveled from my pencil line. We always measure from the pencil line, not from the bottom of the paper, from the pencil line. The distance traveled by the die from the pencil line and the distance traveled from by the distance from the pencil line to the solvent front. We divide the two of them and we will end up getting our retention factor. And then we can use retention factor to identify what pigment is present. Over here, this is my mixture, M. In M, I can see three dyes, blue, red, and I can go ahead and see blue, red, and green. So over here, see, this is dyes separately. I have taken the dyes D1, D2, D3, and D4. This is my mixture, and these are the individual dyes. So in our mixture, if you take a look, dye number 1 is present, dye number 3 is present, dye number 4 is present, but there is no dye number 2, right? So this is how also we can go ahead and separate out a mixture and identify which dyes are present within that mixture. Making sense? Everything is clear regarding chromatography?
Yes.
Okay. So this is basically a topic of your elements and your mixtures and your compounds, and this is the separation chemistry that we have to do. Give me a second, Aram, let me just make sure that there's nothing left. Kiram, I think we have covered everything we need to cover in this topic. So now let's go ahead and take a look at a few questions. Give me a second. Let me just share the screen with you. Question says, a student uses paper chromatography to investigate the dyes in 5 different means, V, W, X, Y, and Z. This is what she uses: a beaker, piece of chromatography paper, a solvent, and inks W, V, X, Y, and Z. Describe how the student should set up and carry out her experiment. You may draw a diagram to help with your answer. So, Anam, go ahead and uh, draw a diagram on a piece of paper. Send me the diagram as well, and along with that, write down the answer. Describe the steps of how she's going to carry out the experiment using this equipment. Are you done?
No, miss, I'm writing it. Then I'll have to draw it as well.
Are you done?
No, miss, I'm drawing it, but where should the solvent line or the solvent be, like, should be placed?
The solvent will be in your beaker where you're going to place your paper.
Okay, okay.
Okay, Aram, do one thing. You can finish making a diagram and write the answer on a piece of paper and then send me the picture of it. Okay?
Okay.
Okay? Okay. Okay, Arham, we will go ahead and we will stop it over here for today. And then inshallah in the next class we will continue on with the topic. All right?
Okay.
Okay, thank you so much, Aram. I'll see you in the next class. Have a good day.